Most of the time, we want maximized light that's coming in through the window in order to make our interior space bright. But we want to sometimes reject the heat that's coming in to the building for the warm climate, especially to prevent the interior of the building from being overheated. Um, but in cold weather, we want to welcome the heat as well in order to heat up inside of the building. So we apply the low-in coating in a differentiated manner based on what kind of climate there is. Uh, for the warm climate, let's look at this light spectrum and target um, uh, entrance value for the light spectrum. For the warm climate, we want to reject as much of the solar infrared portion of the light spectrum. Therefore, only this portion is where we want the light to be entered through the window. Therefore, we locate the low coating on the outer side of the layer, so that the glazing transmits as much of the light as possible, while the low coating reflects the solar infrared radiation toward the outside. However, for cold climate, we want to include that portion as much as possible. In order to achieve that, we locate the low coating on the inner side. In that way, the low coating kind of works in the opposite way, rather than reflecting the solar infrared radiation coming in from the outside. It reflects the radiation that's coming in from the inside back into the interior space. Visual light transmittance describes the percentage of visible light transmitted through the glass. Lower VLT might mean a slight discoloration or dimming of light through it, which means usually bad. Therefore, we want to maximize VLT, and we usually want to minimize the solar heat gain coefficient. There are many different ways to control the solar heat gain coefficient. It includes using the Lowy as we just discussed, and it also includes the tinted IGU. Therefore, what we also want to take a look as an important parameter while we are selecting a glass is the LSG, which is light to solar gain factor, which represent the proportion between the visual light transmittance compared to the solar heat gain factor. Therefore, the higher the number we would like to prefer. Like a sound or water, heat flows and follows through the weakest link of the resistant line, and the heat energy that you wish to maintain in or out will flow through the little tiny hole when it is there. In this case, the study shows how a small tiny portion impacts the overall heat transfer. Image on the left represents the well-designed detail with the proper thermal break placed on the portion of the connected bolt in order to prevent the heat flow through the connection bolt. You can see that the temperature gradient is being created while maintaining the inner portion of the mullion nice and warm when you look at the legend on the right. If we look into the image on the right, which represents the design without the thermal break at the point that it should be, and is the geometry of the thermal break, which is rubber material replaced by the aluminum, and this immediately shows how much of the heat is transmitted through this little bit of hole. Now the temperature at the back of the mullion is almost to 0 degree, while the proper design is maintaining the back of the mullion to be almost 20 degree. Therefore, this design on the right without thermal break will create a problem such as discomfort for the user who is located here, and it will also start to create a condensation for the surface of the mullion. And notice that the transfer of the heat has increased from 5 watt per meter square Kelvin to more than 10 watt per meter square Kelvin. The heat transfer has been doubled compared to the original design. Here are the summary of what you should be aware of when you are designing the building envelope. You should first find out what the problem is and find out how big it is, and you can turn your attention to it and fix it through an iterative process which involve continuous simulation ideally, and you should look at the climate data and think about what think and understanding what the climate is, and it will change the design based on the location. The environment should be the first driving factor for the design. And last thing that we talked about is like sound or water. Heat flows through the very least portion of the resistance. So always try to make the insulation continuous in order to avoid the thermal bridges. And next point, reduce the exposure area to outside, decrease the amount of surface area, and also control the window to wall ratio and eliminate the unnecessary window area in order to save the energy cost. And lastly, limit the number of dividers or unnecessary ornaments which will increase the fenestration area and unnecessary thermal bridges, which will also increase your solar heat gain equation to be higher. And lastly, let's talk about an example of a more complex system which uses the same principle that we discussed in the previous portion of the class. Most commonly used system that is widely known is the double wall system. The basic concept is pretty simple. It is to provide an additional skin on the outside of the existing one in order to increase the thermal resistance by that much. It requires a proper maneuvering based on a season, such as closing it off during the winter in order to trap the heat and providing a continuous ventilation to prevent the interstitial space from being overheated during the summer. And recently, a thin double wall system is also widely being used due to the advanced maintenance technology. In here, by the use of the double wall system, the simulation result shows that a drastic decrease of heating energy exists, and the overall energy usage is being decreased almost 10% compared to the baseline. This CFD also shows the micro comfort control function of the double wall, while a single wall envelope for both of the summer and winter creates discomfort from the surface of the glass being hot or cold and create a radiation imbalance for the occupants. But while by creating additional layer that blocks the direct interaction of the human body to the cold surface, it increased the level of comfort. And this is the case study for another complex design scenario, and you can also use the method of PNB analysis methods that we learned at the second class, and you can simulate it. And if you are worried about the space being overheated and some portion of the space being proportionally hot or cold, you can directly take a look at how the people are feeling comfort based on controlling the input that we discussed, such as the closing value. So you can directly determine the people at certain location are experiencing discomfort at a certain time, and you can modify your design based on the simulation result.